Welcome to the solutions to the electrostatics problem set, problems number 24 through 28. 24, if you are given three different capacitors, C1, C2, and C3, how many different combinations of capacitance can you produce using all your capacitors in your circuits? Well, I came up with 8 different combinations. Let's take a look. The first combination would be if all three were in series, and it doesn't matter the order that they would be in. The second combination would be all of them in parallel with each other. Again, doesn't matter in which order. For combination 3, I have C2 and C3 in series with each other, which is in parallel with C1. The next combination, I have C1 and C3 in series with each other, which is in parallel with C2. Now, the last possible in this arrangement would be C2 and C1 in series with each other, which is in parallel with C3. Next possibility, we have C3 and C2 in parallel with each other, which is in series with C1. Similarly, we have C1 and C3 in parallel with each other, which is in series with C2. And for our last combination, we have C1 and C2 in parallel with each other, which is in series with C3. If you think you have another combination that would work, please feel free to share it in class tomorrow. Question 25, can electric field lines ever cross? Explain. And the next question, can equipotential lines ever cross? Explain. Well, I've included a reminder on the electric field lines, equipotential lines concept here. And in this diagram, we have an electric dipole, positive and negative. They would carry the same charge. And the pink lines here are the electric field lines or lines of force. And the purple lines in the diagram are equipotential lines. Well, electric field lines, the pink ones here, can meet at a certain point. In other words, intersect at a point charge, but they can never cross over each other. If they did, it would mean the strength of the electric field is the same for both lines. And since E equals F over Q, and the force is dependent on the distance from the charge, you could never get a spot where two lines of force have the same E value. Likewise, two equipotential lines can never cross. Equipotential even implies that no matter where you are on that line, the potential difference on that line would be constant, equal, equa. So if two lines cross, that means, for example, that a potential of 1 volt would be equal to a potential of 2 volts. And this obviously is not true. Remember that these purple equipotential lines are always perpendicular to the lines of force or electric field lines. And if you go by just that alone as well, then two equipotential lines would never be able to cross as long as they stayed perpendicular to the field lines along the way. Okay? Number 26. How much charge is on each plate of a 4 microfarad capacitor when it is connected to a 12-volt battery? And then B, if the same capacitor is connected to a 1.5-volt battery, what charge is stored? Well, both of these calculations are a C equals Q over V calculation. In both cases, they provide you the capacitance and they provide you the potential difference. You're just solving for Q. So with a capacitance of 4 and a potential difference or voltage of 12, 12 times 4 is 48. Make sure you include micro in your answer since the capacitance was given in microfarads. You don't necessarily have to convert here. If you do, of course, you'd get 48 times 10 to the negative 6 coulombs. Likewise for B, all they did was replace the 12-volt battery with a 1.5-volt battery. So C equals Q over V. Q is 4 times 1.5. That is 6. And that would be 6 microcoulombs of charge on each plate. Pretty straightforward introductory question on calculating quantities involving capacitors. 27. A series circuit consists of a 0.050 microfarad capacitor and a 0.1 microfarad capacitor and a 400-volt battery. Find the charge on each of the capacitors for A, and B, on each of the capacitors if they were reconnected in parallel across the battery. Out of habit here, we should get used to drawing circuits. So we start off with drawing this circuit. We have a 400-volt battery and 2 capacitors in series with each other, as evident by only one path for the current to flow. Okay? So they want to know the charge on each of the capacitors. And what you see happening here in this solution is that the first thing that's being done is to find the total capacitance in series. The reason for doing this is that we know that all capacitors in this series circuit carry the same charge. So if we were to find the total capacitance, knowing the total voltage, we would be able to find the total charge. So we start off over here trying to find the total capacitance, okay? And we have 1 over CS equals 1 over 0.1 plus 1 over 0.05. The common denominator here would be 0.1 CS. That would make this, multiplying each term by 0.1 CS, 0.1 equals CS plus 2 CS. That's a total of 3 CS divided by 3. And CS is 0.033 microfarads. It should be an S, not a 3. C equals Q divided by V. Go ahead and substitute our total capacitance and our total voltage, gives you the total charge. And remember, this total charge remains constant in a series circuit. So the total charge is 13.3 microcoulombs on each plate of each capacitor. For B, now that we're making it a parallel circuit, so we start by drawing the parallel circuit, 400-volt battery. We put the 0.1 microfarad capacitor in parallel with the 0.05 microfarad capacitor. In this particular case, we know that each capacitor gets the same voltage. It's the key characteristic of a parallel circuit. So we know each capacitor's capacitance, and we know each capacitor's potential difference. So we can solve for the Q value on each capacitor. For the 0.1 microfarad capacitor, 0.1 times 400 is 40 microcoulombs. 0.05 times 400 is 20 microcoulombs. All right, lastly, number 28. 3 capacitors, C1 5 microfarads, C2 4 microfarads, and C3 9 microfarads are connected together. Find the effective capacitance of the group if they are in parallel, and B if they're in series. Whenever you hear the term effective or equivalent, it means the same thing as total. They want us to find the total capacitance for these 3 capacitors if they're in parallel for A, and for B if they are connected in series. Well, in parallel is the easiest because all you do is add them together. So 5 plus 4 plus 9 is 18 microfarads. For B, we have to do the reciprocals of the individuals and add them, and that equals the reciprocal of the total. So 1 over CS equals 1 over 5 plus 1 over 4 plus 1 over 9. And probably the easiest common denominator to multiply to get rid of the fractions is 180 CS. That makes our first term 180, our second term 36 CS, our next term 45 CS, and our last term 20 CS. That's a total of 101 CS's. Divide both sides by 101, and we get 1.78 microfarads. Before we started the problem, just a side note here and a reminder that before we even started the problem, we knew we should get an answer that's less than 4. The total capacitance in the series will always be less than the smallest capacitor in your circuit. And indeed, 1.78 is less than 4. All right, we finish our entire unit on electrostatics tomorrow in class with our culminating problem number 29.